Hello, welcome to this clip going through the redox reaction between ethanol and acidified potassium dichromate in the breathalyser kits that it's actually possible to buy. It's the same reaction that used to be used by the police when they were breathalysing drivers, but nowadays it's done via spectroscopy. In common with all chemistry Olympiad questions, you're started off by a simple description and some context, giving you an idea of where the chemistry being tested actually fits into the real world. So in this case, some further information and data is also provided to give it further focus. So let's start with part A. So it asks you in part I to complete the half equation for the oxidation of ethanol to ethanoic acid. And a half equation shows the reduction or oxidation part of a redox reaction. And when you combine them together, a bit like simultaneous equations in maths, they give the overall redox reaction. So obviously we'll be doing this in part II, as you can see. If we take the definition of oxidation number and we look at the number of electrons an atom of an element has involved in bonding, we can see that at first glimpse, going from an alcohol, such as ethanol, to carboxylic acid, such as ethanoic acid, the actual number of bonds that each atom has seems to remain the same. So we have to think of another way of working this out. So if we look at the change from ethanol to ethanoic acid, you go from 6 hydrogen atoms in ethanol to 4 hydrogen atoms in ethanoic acid. But if we look at oxidation another way, as either the gain of oxygen or the loss of hydrogen, you can start to see what's going on here. Both observations about the change from the number of hydrogens and oxygens in ethanol and the number of hydrogens and oxygens in ethanoic acid support this. So if you lose 2 hydrogens from ethanol and also use up 1 water, that means you have 4 hydrogen ions being created. And 4 electrons are also released to balance the charge on the right-hand side. So we now have our equation. From this next part, it asks you to complete a half equation for the reduction of the dichromate ion in acid solution. So this is a little bit easier because you've got a set of steps you can use to balance this half equation. So first of all, let's look at the species. Let's start with chromium. So because there's 2 chromiums on the left-hand side, you have to have 2 on the right-hand side. Now, we've got 7 oxygens on the left-hand side, so that means you need 7 waters. So if you look at the number, the oxidation number changes going from +6 to +3, you can see that there's 3 electrons gained. However, there's 2 chromiums, so therefore this happens twice. So in actual fact, there's 6 electrons gained. And therefore that requires also 14 hydrogens to balance all the charges out and also support the production of 7 water molecules on the right-hand side. Now to combine these two, what you've got to do is to try to cancel out the electrons. So if you multiply the top equation by 3 and the bottom equation by 2, so we end up with these 2. So now what you need to do is cancel the electrons and any other species that turn up the same number, that turn up on both sides of the equation. So we've got H plus to deal with, and we've also got H2O to deal with. So now we can combine everything, which gives us 3 moles of ethanol, 2 moles of Cr2O72-, 16 moles of hydrogen ions, converting to 3 moles of carboxylic acid, this is ethanoic acid, 4 moles of chromium, 3 plus ions, and 11 moles of water. So the next part of the question asks us to assume that the acid used is sulfuric acid and the dichromate salt is potassium dichromate, asking you to write a balanced equation for the reaction. So if we think about H2SO4, it's got two hydrogen atoms in it that can form hydrogen ions, so it's got two acidic hydrogens per molecule, the H2SO4. So if you want 16 H pluses, therefore you need 8 molecules of sulfuric acid. So on your reactant side, you've got 3 ethanols, 2 K2Cr2O7s, and 8 H2SO4s. On the right-hand side, you still have your 3 ethanoic acids, but remember that chromium is in the 3+ oxidation state, and the sulfate ion is in the 2- as its charge. So therefore, a 3+ charge and a 2- charge have to be added together in a ratio of 2 to 3. So that allows us to balance it out and still have the 11 H2Os. So if we now move on to part B. So in this part we know that the plastic bag in the breathalyser kit is inflated with 1,000 centimeters cubed of breath, which is the same as 1 decimeter cubed. And when the bag is connected to the tube containing the dichromate crystals and the breath is expelled, the crystals change colour as they are reduced. And it says the proportion of the crystals that change colour indicates the amount of alcohol present. So the current legal maximum blood alcohol concentration when driving in Britain is 80 milligrams per 100 centimetre cubed of blood. So what they want is the corresponding breath alcohol concentration in micrograms per 100 centimetre cubed of breath. So just to check our conversions, 1 microgram is a millionth of a gram, which is obviously 1,000th of a milligram. Now if you have 80 milligrams per 100 centimetre cubed of blood, that would equate to 800 milligrams per 1,000 centimetres cubed of blood. But blood alcohol is 2,300 times breath alcohol. So therefore breath alcohol is 800 over 2,300 milligrams per 1,000 centimetres cubed, which is 348 micrograms per 1,000 centimetres cubed, to 3 significant figures. On the next part it says, assuming the tube must be able to test breath to at least 3 times over the legal limit, what mass of potassium dichromate should the tube contain? So that needs 3 times 348 micrograms of ethanol for the legal limit. So doing a quick conversion to grams and then dividing by the molar mass of ethanol, it gives you 2.269565217 times 10 to the minus 5 moles, that should be. Okay, so now what we need to do is work out the mole ratio from our previous equation of potassium dichromate to ethanol. So to get the number of moles of K2Cr2O7, you need to multiply the number of moles of ethanol times 2 over 3. So that gives us 1.51304347 times 10 to the minus 5 moles. Now bearing in mind that the molar mass of potassium dichromate 6 is 294.0 grams per mole, so we can work out that it's 4.45 milligrams to 3 significant figures of K2Cr2O7 that's actually needed. Now the final part, what colour change would you expect for a positive result? That's simple recall, and that's obviously orange to green. Okay, so that's the end of this clip. Hopefully it's been a useful extension exercise on alcohol's oxidation from the first year. So until next time, thanks for listening and see you soon.